Hey all, welcome to Chapter 14, Chemical Kinetics. This starts a brand new chapter and it's about chemical kinetics. I'm going to actually let you read section 14.1 on your own, but it's actually quite interesting. It talks about how the author's children catch lizards. And yeah, very interesting, a little disturbing, but we'll not worry about that part. Moving on. Just one thing that you should take from there, the history. Ludwig Wilhelmy was the first to measure rate of reaction carefully, so he's the one that gets credit for it. Basically what he did was he measured how fast sucrose hydrolyzed, which means it breaks up with the addition of water, into glucose and fructose. The reaction occurred over several hours, and what he saw is that it depended on how much sugar was present, which gave us our first item that depended on reaction rate, which is really cool, but we'll get into that a little bit later. So let's jump right into 14.2, chemical kinetics. Chemical kinetics, basically we're talking about how fast a chemical reaction occurs. So if we look at this picture here, this is the same one given to you in your book, and on the left side, that would be this side, we have a reaction that is fast, and on the right side we have a reaction that is slow. As you can see, they both start at time 0, then after about like 16 seconds you can see only one product over here, whereas in here we have 1, 2, 3, 4 products, so obviously that one's moving faster. Then as you continue down and see at the end, we now have only 3 products. But here we have all products. Everything has been converted to products, which tells us that's a really fast reaction, and that's after 46 seconds, as you can see there. All right, so let's go a little bit deeper here, and let's talk about definition of reaction rate. This tracks our changes in the amounts of reactants and products. Usually we track that change in molarity, because molarity is our concentration, and remember, molarity is moles per liter. That'll be coming up a little bit later. So our formula, if we have a reaction here, A goes to 2B, our rate is just like we would figure our speed in our car, where we take change in distance over a change in time. It's the same thing here. So we're going to take change in concentration of A. Remember that these brackets, and maybe we don't remember, but these brackets mean molarity because they mean concentration. So that's something we need to remember. Our delta obviously means change. We don't want to forget that. Down here, so we've got change in concentration of A over change in time. Now, as you can see, for our reactants, we put this negative sign out front. That negative sign is because the reactants are going to be used up, and we always want a positive rate. So if we take final concentration minus initial concentration, that will give us a negative number for our reactants, but we want it to be positive. So we go with the negative sign out front. Then, as it relates to the products, we can see that we take change in concentration of B over change in time. And there's something additional here that we have added in, and that's that 1 over 2. And that 2 that's on the bottom there is because of this 2 in front of our 2B. We're saying that for every mole of A that breaks down, we form 2 moles of B, so we've got to put that into our concentration just a little bit. So we can look at that in a handy-dandy graph. This is very similar to what we had. H2 plus I2 gives us 2HI. They took off I2 so we wouldn't have to be confused by another line. So as you can see, this line here, the green line, is our concentration of H2. And as you can see, it is decreasing over time. Our other concentration, our red line, is our HI concentration, and as you can see, it increases over time. And so what we can do is we can find our change in delta H over our change in delta T by taking how our concentration changed over our time. Also, if you look at the slopes of these lines, this gets us back to the stoichiometry of it all. All right? Notice how this line has a steeper slope, if you will, than the first line, than the green line. And that's because there are twice as many H highs. Alright, take a couple of seconds to soak that in and kind of look on that. Okay, so let's look at some things to remember here. First off, remember that reactants are consumed in a reaction, so we are going to what? Since reactants are consumed in the reaction, we're going to put a negative sign out in front. And we're going to say change in our concentration of our reactants. I'm just going to put R there over our change in time. That's that. Products are produced in a reaction, so we're going to just take delta of our products over delta T. All right? And this must be based on stoichiometry. All right? So we have to use stoichiometry for these rates to relate to each other. Now, average rate of reaction is calculated just as you would expect. The average rate of a reaction decreases as the reaction progresses. Why is that? Why is that? Our average rate of reaction decreases as the reaction progresses, and that we're going to cover a little bit more in detail later, but basically what we have is that the reactants are being used up. So there's less reactions to happen. And we'll talk about collision theory in another video. So for right now, let's just say our reactants are used up, thus making our reaction harder to do. So now, to find the instantaneous rate of reaction, we can do this by finding the slope of the tangent line to the curve at the point of interest, which is what we did right up in here in this little area right there. All right, we have this generic reaction, little a, big A, plus little b, big B, goes to little c, big C, and dd. So what we can see is we've just basically written our formula for relating those all together. The best part about this is, so knowing the concentration of a reactant or a product at a certain point of time, we can find anything else at that point in time, which is really pretty handy. But there's a drawback to this. We cannot predict the rate at a future time. So let's take a look here at an example. So we have hydrogen peroxide plus 3I gives us, or plus 2H pluses gives us I3 minus and 2 H2Os. In the first 10 seconds of the reaction, the concentration of I minus drops from 1 molar to 0.868 molar. Our first step is to calculate the average rate of this reaction. So all we're going to do is, we know that's I minus, so we're going to just plug it in and solve. So we know rate equals 1 over 3, and it's going to be negative because it's a reactant, delta I minus over delta T, and we're just going to plug it in. So we've got negative 1 over 3, and we're going to take final minus initial, so 0.868 minus 1.000, whoops, parentheses, wrong, over 10 seconds. And so right now, when we do this calculation, we're going to have molarity per second is our label here for our rate, which makes sense. So 0.868, and we're going to subtract 1 from that, and we're going to get 1 over 3 still. And now we have negative on top, 0.132 over 10. So we divide that by 10. And then we're also going to divide that by negative 1/3, which is going to give us 0.0044. And I've ran out of room here, which is unfortunate. So we'll just make this a little bit smaller for right now and move it over. So 0.0044. and that's molarity per second. So that's our rate. And now, how do we compare that to H plus? And so, very simply, we're just going to compare. We know that rate equals negative 1/3 of this guy. Ooh, bad writing. Is equal to, if we're looking at H, we've got 1/2, right, of this guy, delta H plus, and delta T. Delta didn't really show up there. So we know this one right here is 0.0044. So to solve, we're going to just multiply that bad boy by 2. Obviously, we're trying to isolate the 2, right? So if we put this on each side, lose that rate for a second. All right? And so when we multiply that baby by 2, we come up with our rate for delta H. A change in delta H over delta T is going to be equal to 0.0088 molarity per second. All right, rolling on. So our conceptual example there, for the reaction of A plus 2B goes to C under a given set of conditions, the initial rate is 0.1 molarity per second. What is delta B over delta T in the same set of conditions? So we're just going to divide that baby by 2. So our answer should be A. All right? Because we know that that is for 1. All right? So the last part of this section is how can we measure reaction rates? In the very first experiment with Wilhelmy, they used polarimetry, and that's how light rotates. It goes into a little more depth, but we're not going to use it that much in here, so I'm going to save that explanation for if you want to read about it. We can also use spectroscopy, which is measuring how light is absorbed. We can do this for very short reactions because our light travels fast. I want you to fill in this section about how a spectrometer works. All right, so come back to that after you've read about it, because that is actually how we're going to measure most of ours. We're going to do a crystal violet reaction to see its reaction order based on how it reacts with sodium hydroxide. You can also measure pressure changes just by using a barometer or a manometer. For slower reactions, you can take aliquots, which is samples. The word aliquot just means a sample. So you can take a little sample and you can either use gas chromatography, so you can look that baby up. You can use mass spectrometry, which also you should look up, or you could use titrations. We are going to actually use these a little bit later. All right, thanks. Have a great night.